Hi, I am Praveen. I will be presenting the paper Multi-Agent Diverse Generative Adversarial Networks, also known as MADGAN. So the outline of today's talk would be that we will first look at an introduction to generative adversarial networks, and then we will look at the popular GAN models. Then we will look at the problems that we have while training GANs, and especially we will look at the problem of mode collapse, and then we will look at uh, the architecture of the MADGAN, the paper that we are reviewing today, and see how they are solving this problem of mode collapse. And then we'll look at the experiments that they have shown using their architecture. So before we talk about the paper, let's have an overview of generative adversarial networks. So you can think of a generative adversarial network. So there are two components to this. So there's a generative part and an adversarial part. So the generative part is where you are learning to map from a latent space, which is a lower dimensional latent space, to a higher dimensional target space that you want to learn. That's a generative part. And there is an adversarial part where you are making two neural networks compete with each other adversarially and try to get to an objective. So the input to here is noise to the generator, which is sampled from a noise from a usually a Gaussian or a normal distribution, which we call as PZ, and we pass this to the generator, which will first reshape this noise into a 2D image as 3D with a image and depth, and then we apply a series of deconvolutions to get to the required image shape that we want. And these images are the generated images, which are the images that are from the from a distribution called PG, which is the images that are generated. We want these images to be as close to the real images, which come from a target distribution PD. So we want this PG and PD to be as similar as possible, and the objective of the generator is to do that.
So I have a question. So like when you reshape your 4x4 and you have 1024 of those, right? So 16 times 1024. So which means this noise would be 16,000 dimension or something? Or how do you do that?
No, usually the input is a 100-dimensional noise input, and then you reshape it to a, let's say,
10 by 10 or something?
yeah, and then you apply the 2D convolution, converse of convolutions, which you call deconvolution or converse, yeah, upsampling, and then you apply a series of upsamplings, not upsamplings actually, deconvolutions.
Yeah, so I mean, you take this 100-dimensional vector and then you reshape in just one of the image, 2D, and then you do the decon to get these things.
Yes.
Right?
Yes.
Okay.
And the generated images and the real images are passed to a discriminator, whose job is to distinguish between the real images and fake images. So the output is a binary output. So as I was saying, there are two distributions. One is the PG, which is the images that are generated by the generator, and there is PD, which is the target distribution that we want to learn. So here I have a representation of the same. So if you see here, the input, we have a 2D space, and the green distribution represents the data or the target distribution that we want to learn, and PG is the distribution that is learned by the generator. So here uh, the PG is similar to PD, but they are not exactly the same. So the generator is trying to learn a distribution which is as close as possible to the target distribution that we are trying to learn.
So yeah, the image is like very simple, just two-dimensional,
Yes.
two numbers.
Yes.
Right? So you have distribution of the generator and the distribution of the discriminator.
Distribution of the data.
And you want to make them similar. Okay.
Yeah. So the objective of the generator is to make these samples as close as possible, and the discriminator to distinguish them. So if you look here, so the samples that are generated by the generator Yeah, you can see it on the 2D plane, which are the samples from the distribution that we want to that is learned by the generator, and the green dots represents the samples that are from the real data. So if you are learning to generate images, then these samples would be different images that we are trying to learn. And we make this generator and discriminator play what is called a min-max game, where both of them are competing with each other. The generator trying to fool the discriminator by generating images which are as real as possible, and the discriminator trying to distinguish between real and fake.
And this distribution has only one mode, second mode.
Yeah, here you have, actually, if you look at the green distribution, it has two close looking modes, one here and the other here, but the the generator has learned to generate one mode better than the other.
So it's generator gen 1 only.
Yeah.
So that's called mode collapse.
Yeah, when okay, so we will talk about mode collapse, and I have other visualizations of mode collapse as well, which would explain that better. So coming to popular GAN models, so one of the first well popularized GAN model is called DC GAN model, which is called deep convolutional GAN, where deep convolutional networks were used on both the generator and the discriminator. So here is a representation of the same. So we take an input noise, reshape it, and then generate an image, which we pass into the discriminator, which will learn to distinguish between real and fake. Next came some other extensions to the general GAN models, which were Wasserstein GAN and loss sensitive GAN. The changes here were mainly about how to calculate the loss. So there was no change in the architecture as such, but there was changes in how the loss is computed at the discriminator. Then other architectures that became popular was some of them were AC GAN and Info GAN. So here the difference is in AC GAN, which is called auxiliary classifier GAN. In the discriminator, the job of the discriminator is not only to distinguish between a real and fake image, but should also to classify the class of the image. That's why it's called auxiliary classifier GAN. And then came Info GAN, which is information maximizing GAN. Here, the theory behind the information maximization was applied. So basically, we will look into the details of Info GAN, because this GAN was used in this paper. So if you look at a vanilla GAN, you just sample some noise, pass it to a generator, and it generates some images which are passed to a discriminator and which are discriminated whether it's real or fake. But in Info GAN, the difference is that along with the noise Z, we also pass another input called C, which is called as code, which is passed to a generator. And the task of the discriminator is not only to discriminate, but also to reproduce this code that was passed in. The idea here is that when you do this, the GAN model, both the generator and discriminator, will learn those features from the latent space, which are more relevant to the generative process than just giving some random noise.
But what that has to do with C?
So C is if you are reproducing C again at the discriminator, so it's like a reverse of autoencoder. So what we are trying to do here is that we are trying to learn important features from the latent space, which are represented by C, while doing this generative process.
So I mean, you are generating these features so that you are able to reproduce C. Right?
Yes.
C is the input.
Yes.
And you want to get C back.
Yes.
So you learn not only from a noise to generate an image, which is as realistic as possible, but at the same time you input C and you are able to reconstruct the C back.
Yes.
So this is a robust model.
Yes. So there are many problems with training GANs. One of the main problems which is there in almost all the GAN models that are proposed is called mode collapse. So which is addressed in this work. So this representation is a intuitive visualization of the mode collapse, where you think of it as, so the distributions here are the target distributions that you want to learn, and it has two modes. One of the modes has more data samples, and the other mode has few samples. So in this case, if you have a single generator, the generator might be more tentative to learn the mode which has more samples than the mode which has less samples. And this will result in a scenario where the generator will only learn one of the modes because it has seen that mode more often, and then collapse to that mode where it will only generate samples from that and not learn to generate sample from the other mode. The other problems of GAN training includes difficulty in optimizing the generation, optimizing both the generator and discriminator, problem with counting. So here if you see, these are the images that are generated from ImageNet, and these are the images of dogs. If you see the images that are generated here, the generator has learned to generate something which resemble a dog, but it doesn't know how many eyes does the dog has, or in some cases how many ears. So it generates more of those, and this is one of the problem with GANs. And the other problem is with perspective. So even here, if you see, there are these, for example, this image, there is one dog image, but the perspective is not properly maintained. So there is one face which is looking this way, and the other face which is looking this way, and it's not able to learn the correct representation, because in the training data you have images where dog is looking at one direction and also in the other direction. So it's not able to learn that perspective. Other problems include problem with global structures, and there are many other problems with GAN training. But we are in this presentation we are mostly interested in mode collapse. So I'll try to explain what mode collapse is. So assume that this is your target distribution. Here you have samples which are distributed in such a way. You can think of this as there are 8 different clusters, and there are samples belonging to each of these clusters. If you think of this as a distribution, each of these clusters will represent one mode. And if you train a normal generator, this is what you could observe. So initially the generator will learn to generate one cluster or samples from one cluster or a mode, and then once the discriminator learns to distinguish the samples from that mode, the generator will skip to another mode and starts generating samples there, and so on. So it jumps from one distribution, one mode to another mode, and doesn't learn the overall distribution. So the problem here is that the generator tries to fool the discriminator, and it keeps jumping from one mode to another. There are different solutions that are proposed in different papers. So one of the general solutions that is used for avoiding mode collapse is in improving GAN training. Here, what one would do is to train the discriminator initially for some iterations, so that the discriminator would learn to distinguish between different modes, and then start training the generator. It proved to be useful in some scenarios, but not in all. The other kind of solution for mode collapse is to enforce the generator to learn these diverse modes than just expecting the discriminator to learn better. So in this work of MAD-GAN, they have used this approach where they have forced the generators to learn different modes. Coming to MAD-GAN, which we are discussing today, the aim of this paper is to overcome mode collapse by forcing the generators to generate different modes. The approach that they have followed here, they have proposed 2 different approaches where in both of them they have multiple generators and one discriminator, and they force each generator to generate different samples. And for this, to force the generator to generate different samples, they have defined 2 different objectives. The first objective is called similarity based competing objective, where they have made changes to the way you train the generators, where the generator's objective is not only to generate real looking images, but each generator should be generating images which are not similar to the images that are generated by other generators. The other objective that they have defined is called generator identification based objective, where they have not changed the part of the generator, but the change is in the discriminator. The discriminator not only should distinguish whether it's a real image or a fake image, it should also detect or identify the generator which generated the specific image. So the architecture of this is as follows. if you, if you compare this with a normal GAN model, so we take noise from a noise distribution and pass it on to the generator, which would generate an image, and then we pass that image and some real samples to the discriminator, which will learn to discriminate between the real and fake. In here, the addition to that, you have multiple generators which will generate different samples, and all of them are passed to the discriminator. And when you are using the similarity based computing objective, you you change the objective of these generators to generate distinct images. In this architecture, one thing what they have done is that they have tied the weights. It means that all these layers in all the initial layers of all the generators share the weights, and only the final layer of the generators have different weights. This is in the when we are doing a similarity based computing objective. When in the generator identification based objective, the change in the discriminator is that the discriminator will now have an output of k plus 1 classes, where k are the different k generators that you have, and the k plus 1 output is the output which says whether it's a real image or a fake image. So let's look at how they have enforced the diverse modes. The first one is, as I was mentioning, the similarity based computing objective, where they change the way the generator learns to generate the images. So the idea, what we want here is that the different generators must generate similar samples, and this dissimilarity is computed for a specific task. That means that the similarity that you function that you define will change from the different data sets that you use. So here is the intuition. Suppose you, again, if you have a target distribution where there are two modes and you have two generators, then the way you want to train these generators is to force one generator to the one mode and the second generator to the other mode. To do this, the constraint that they have imposed is as follows. So let's look at it part by part. So Gi of Z represents the image that is generated by the ith generator. J of Z represents the image that is generated by the jth generator. This function here is used to map the generated image from the generator to a feature space. This feature is extracted from the discriminator which you have trained. So these features are compared between the images that are generated by the ith generator to all the other generators, and if they are very similar, if the image generated by the ith generator is very similar to the image generated by all the other generators, then you have high similarity, and that would result in a high penalty to that discriminator, to that generator. So that would increase the loss of the generator, and that would force the generator to generate different looking samples, which are different looking samples from the other generators.
And also, you should talk about also the other second part,
Yeah.
right?
Yeah. So the output, the constraint here is that the output of the generator I, the output of the discriminator for generator I should always be greater than or equal to the output of the generator J at the discriminator. All the output of all the other generators plus this constraint term that we are introducing.
So discriminator should say that image generated by ith generator is much more real than
Others, yeah. So the algorithm that they follow is that for every generator Gi, they sample noise and pass it to the generator, and they generate the image. And then for that image, they calculate the corresponding feature vector. Now pass the same sampled noise to all the other generators and extract these features. For those images. Now you compute the similarity between feature I and all the feature J's. If this similarity is very high, you mean that you want to then punish the generator I more. So you update the generator I's loss depending upon this similarity. If higher the similarity, higher is the loss. And in this approach, there is no change in the way you are training the discriminator. So, and here I just I'm showing the algorithm that they have followed and which I have explained here. So the other objective that they have defined is called generator identification based objective. Here, the inspiration is from semi-supervised GANs, where at the output, the output of the discriminator, it's not binary, whether it's a real or fake, but it should also detect the generator which has generated the image. So the objective of the discriminator here is to maximize the entropy uh, of H. H here is the negative maximize the expectation of negative cross entropy, where this term dx given these parameters is the output of the discriminator, and this is the ground truth, or the actually this is the direct delta function of k plus 1 output.
It's like a
One hot vector, and we want to if we are actually maximizing the negative cross entropy, which means that we are minimizing the cross entropy between the output and the expected output.
So one hot vector will tell you
which generator has generated that image, and if it's a real image, then whether it's real or fake. So the intuition behind this idea is that if the discriminator has to learn to distinguish between different generators, then it will push the generators to generate different looking samples, so that it becomes easy for the discriminator to discriminate. So this change in the discriminator will force the generators to generate different looking samples. And in this objective, there is no change in how the generators are trained. Now we will look at the experiments that they have done to show their results. The first experiment, that is a toy example, where they have training data like this. So here there are 18 Gaussian distributions. They have generated the samples here using a Gaussian mixture model with 18 Gaussians. And the way they have generated this is that they made sure that there are 3 clusters, and in each cluster there are 6 Gaussians.
So in this one, each sample is just 2D.
Each sample is a 2D, so it's a 2D space. And this is the training data. And they trained their GAN model using this training data. They show the results that if you are using a vanilla GAN without any modifications, this is how a generator would learn to generate the samples. As you could see, it was not able to capture all the different modes or the different clusters, and it's only able to generate samples which lay in the closest distance between all the 3 cluster centers.
So I have a question here. So that's what we want. We want to generate these images of this data, which is this distribution, right? So practically, how would you train the gain? Like, so gain, as you mentioned, your generator, discriminator. So you would have the input result from noise. So does this mean that you would sample that noise from this kind of distribution?
Yeah, so you have a Gaussian mixture model of 18 with 18 Gaussians, right? So you sample data from that Gaussian mixture model, and that will be your ground truth or the real samples. And you sample randomly from this 2D space, and that will be your noise. That will be your sorry.
Yeah, so we are talking about, we know we want this, right? So the question is, like, what will you input to the generator? So the noise, will that noise be sampled from the 18-dimensional Gaussian?
No. Noise can be anything from any distribution. So the output of the generator should be a 2D output. So that 2D output will then be passed to the discriminator, and the real samples will be the samples that are sampled from these 18 Gaussian mixture model. So then the discriminator will learn to distinguish between the real and the fake, and then the generator will learn to generate samples from the real distribution, which is this 18 Gaussian mixture model. So if you are using a vanilla GAN, these are the outputs that you have. and then they applied batch normalization to the GAN model, and this is and the results are like here. So the batch normalization helps the generator to learn the different modes, but what they have observed is that when you apply batch normalization, the mode which has less samples will not be learned.
Just on the, everybody knows batch normalization. If you don't know, please look at the lecture because that's the minimum you need to know in this class. Okay. Yeah.
Okay. So, and here are the results when they have used their approach. So they have trained their model with 3 different generators, and what they have observed is that each generator learns to generate samples from different clusters. The next experiment was on image to image translation. So here the input to the input is the sketch of an image, and the output of the generator should be realistic looking images by applying texture and color on the sketch. So these are the results that they obtained when they were using competing objective, and in all their experiments they have used three generators. So as you could see, the generators are not only are able to generate different looking samples, but they are also realistic. They applied the same the generator identification objective on the same problem, and here are the results. So again, even the generator identification objective was good enough to learn different looking to make generators generate different looking samples.
So one is generating like green.
Yeah, so one is generating green. So the columns represents the images that are generated by different generators, and the first column is the input. So similarly,
This input is, can you go back? So input is like conditioned.
Yeah, conditioning. So noise along with the conditioning, which will represent the sketch.
Because people need to know that. So because you talk about just noise, so in addition noise, you can put other input.
Yeah.
And in this case, you are putting
The sketch, yes, input.
which you concatenate.
Yeah. And the next and in the same problem, image to image translation, the next data set that they have worked with is this places data set, where the input to the generator is the image of a place at night, and the generator should learn to generate the images of the same place at day. So again, the input here, the conditioning here of the generator is the input is the column 1, and these are the images that are generated by 3 different generators, and this is when the competing objective is used. Similarly, here are the yeah.
Can we comment anything about the mode we learned from it? Like, it just says
Yeah.
that, okay, 3 different.
Yeah, I will come to that. So here, okay, if you look at the first image here, so each of them are generating different colors. So you can think of that each color being one mode. So the generator 1 is trying to generate only blue looking bags, and the second one is generating brown looking bags. Here you can see, so here all the images, all the bags that are generated by the first generator have a specific texture. These look more velvety. In the second, third one, they look more like a leather. So you can think of these as different modes that the different generators have learned to generate. And even here, if you look, the first generator has learned to generate day images with little bit of clouds, but in the second generator, if you look at the images, they have more clouds, and the next one is much more, I mean even more clouds. So these are the different modes. So we don't know the real modes that are there in the distribution that we are trying to learn, but these are different modes that you can at least visually see here. Yeah, and the next experiment that they have performed is phase generation using InfoGAN. So, so here you see that these each image in the each column. This image is the images that are generated by generator 1. These are the images that are generated by generator 2, and these are the images by generator 3. So here each column in these individual images represents the images that are generated by InfoGAN when different codes are used. So I was referring to C, which is the input to the generator in the InfoGAN. So if you have different Cs, these are the different images that are generated by InfoGAN. And the next row represents the next 3 rows represents the images that are generated by the generator. So one thing what they have observed is that one of the first generators, when we are using different codes, the images that are generated will have the so for example here there is variation in terms of the facial expressions. Here in the second generator there is a variation with respect to the hairstyle, and in the third one there is a variation with respect to the amount of lightning that's there on the face. So all the three different generators have learned to generate samples which are distinct looking, but not only distinct looking but also realistic in this case. And the next experiment that they have performed was on generating facial images using DC-GAN. So the first column here is these are the images that are generated by one of the when you are using a generator identification objective, and they have used the Celebi dataset here. And similarly, these are the images that are generated when using the competing objective. And they have also performed experiments on image generation using ImageNet dataset. And in here they have shown only results when the generator identification objective was used, and they have mentioned that they did not get good results when the competing objective was used.
So, okay, so I have a question. So one is that DC gain is like a vanilla gain, right? And then info gain has this additional C vector. So it's known that info gain always generate better images compared to vanilla gain.
Yeah, so in the one of the contributions of InfoGAN is to generate more realistic and better looking images, and they also say that they provide a theoretical backing of why that would work, because you have this the code that you are trying to learn, and they provide a information theory based theory which explains why the InfoGAN would work, and it gives much better results than a general vanilla GAN.
So what's the point then to keep people to keep using DC gain?
So this is just for a comparison to show how it would work on when you use. So the first paper which was published on face generation used DC-GAN. So this they have just used that to have comparison to that baseline works. And the final experiment that they have shown is the unsupervised representation learning, where they have used the SVHN dataset, which is the Google Street View dataset. So here the objective is to find the quality of the features that are learned by the GAN model. So the way you do it is you train a GAN model on this dataset and then extract features from the. So you remove the last layer of the generator and the first layer of the discriminator, and then you generate the images on the trained generators and extract a feature from the discriminator, which is then used to train a SVM classifier. If the features that are learned in this generative process are really good enough, then the SVM classifier should give you very good classification results, because the learned representation of those images are really good. So that's why it's a representation learning that's what they want to check.
So classifier is trained on the generated images?
No, on the features that are extracted from these generated images. So you pass on noise, you generate an image, you pass to a discriminator, and from the discriminator you take a feature vector, and those feature vectors are then used for training the classifier.
Yeah, so that's fine. So which means you train again, it's done now,
Yeah.
and then you can input an image to the discriminator to give you features.
Mhm.
So use those features to train this.
SVM, yes.
And these images which you input to the discriminator, they are the synthetic.
Yeah.
Right? So you train that. Then you want to use that discriminator to classify the real image.
They extract the feature and then train another SVM classifier to see whether these features that they are learned are really good enough in classifying different images or different classes or not.
Classifying again the synthetic images or the real Google Street View.
So at the discriminator, you can pass in both. So they take the whole the data set which has the real images and also the images that are generated by the generator after you have trained, and then they pass into the discriminator and
No, I
extract the features.
understand that. I mean, when you use the discriminator, you have to use both. It comes from the
Mhm.
generator. So it's trained.
It's trained, yeah.
Right?
Yeah.
So this experiment is saying that how well the discriminator has learned the features,
Mhm.
right? So now you dismantle that, and you have a bunch of generated images, and you also have the real images.
Yes. Now you pass in the generated images to the discriminator and take the
get
the features and then
use those
train.
features to do the SVM.
Yes.
And then what do you test?
Yeah, and see how well the classification works.
Train models. Yeah, I mean, so then what is the
So if the SVM classifier is able to really distinguish between is able to classify, then the features that are learned are good representation of that images, and you are able to
I
learn.
mean, that's not a big deal, right? I thought it would be better, bigger test would be that you train on the synthetic
Mhm.
and then test on the real one stream. You see how well it learns very robust feature, which is there's no difference between real and synthetic. But I mean, SVM you can train on any data, right?
Yeah.
Synthetic or real.
Mhm.
So it doesn't. It's not a big deal. So I don't get it if that's the case.
Maybe I'm missing a
Yeah.
point there. Then
Yeah,
I
okay,
guess.
that's fine.
So what they have shown is shown in the results is that when they have used when they have applied this approach, both the competing objective and the generative objective on this task, and here are the classification errors on the SVHN data set. And when they are using 4 different generators, they get the least error, and this is 5. So when you are using a traditional GAN, this the error rate is 22.5, and they using this multiple generators they got it down to 17.5, and they show that this is better. This in using this approach they can learn better representations as they get less errors. Thanks. That's my presentation.
Okay, very good.
Thank you.
Wonderful.